Okay, so I start recording from here. And also the tutorial yesterday, we're still trying to find out where it actually got sent to. It got sent to an email address, and we can't find it yet. So we'll find it hopefully and put it onto YouTube soon. But yes, Elliot, very good. This equals D2, which equals D4. Yeah. So we have essentially our fourth, and here we have our fifth structural constraint. Where's my... Because we could really write these out being like x3 equals D4. And this would be our fifth structural constraint, for example, if we were to do it the long way. But now let's keep going. A sixth structural constraint. What would this be now? X4 equals D4 plus D8 equals D5. Very good. Perfect. X4 equals D4 plus D8 equals D6 plus D5. Oops. Next one. So this is number 7. What's the next one going to be? X5 equals D5 equals D8. Exactly. You guys have got the hang of this. D5 equals D8. So next one. Yep, there we go. So these are the structural constraints. Now, if we look at the lecture slides again, close this now. We also have, let me just save this. We also have logical constraints. And so logical constraints are a little more tricky to extract. I think there was an example of them somewhere. Here we go, logical constraints. They actually arise from the logical flow of the program. And so what that means is that, for instance, if we look at this graph here, like this, sorry, this code snippet, we have I equals 0, and we have a while loop where I has to be less than 100, right? And we can see, for instance, that OK, we have if OK, J++, else K++, OK equals true. So that means at most, because this K equals true, at most, this else statement could be run once. So a logical constraint would be, for instance, see here, this X5 can be executed at most once. So this is why there's X5, which is the execution count of block 5, would be less than or equal to 1. Therefore, as you can imagine, X4, the other branch, would get executed at most, at minimum, 99 times. So could someone tell me what a logical constraint would be for X2? Yes, so this will run 100 times. And if we were to make a little block of this, like a little flow graph of this one, we'd see, for instance, that X2 and X6 would be equal, right? But now with logical constraints, let's see, it's not in the question in the tutorial, but let's see if we can derive some logical constraints from this program. We look at this. So while J is greater than 0, I is less than 10, J equals I. I think this might be a bit too complex to derive. What about this one? W equals 0, X equals da, 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 Y is greater than Z. No, I don't think we can either. But I don't think I'll ask you about these questions. How do we know X5 is greater than less than 1? So let's imagine that we're executing this program And we have to think to ourselves, okay, like the okay variable is equal to false. Like let's imagine okay is equal to false when this program starts executing. How many times would I execute x5 if you just think about what's going to happen? Exactly. But if okay was equal to true when the program starts, how many times is it going to execute? No, no times. Because if okay is equal to false, sorry, if it's equal to true at the beginning, it's not going to ever enter x5 because it'll just do x4 the whole time. Okay, hold on. Where did this? So if we think about this block of code executing, but we just want to think about, like, just purely think about, okay, what are the possibilities? Like, what possible values could okay have before? Sorry, I should write this out completely. Before x1. So like here. True or false, exactly. So we can essentially say true or false. These are our two possibilities. So let's say it's true. How many times will we execute x4? Exactly. So x4 equals 100. Let's say it's false. How many times will we execute x4? Yes. Now, what about that? So the equivalent will be x5. What will x5 equal for these two sort of possibilities? Mm-hmm. And this will be 1, right? So therefore, we can look at this and say, okay, therefore, oops, we know x5 is less than or equal to 1, and x4 is greater or equal to 99. You could also, for instance, put in here 100 is less than or equal to x4. And this is just from looking at the actual code, right? Because if we put this into like basic blocks, you create a graph that would look something like, let's think about the basic blocks. We would have like 1 basic block, 2 basic blocks, 3 basic blocks, here, here, like this, right? Actually, this would have been a good one to put on, to do an example from. So let's do an example from this one then quickly. So I'll move this over here. Da-da-da. So does everyone agree? I'll upload these at the end of today as well. Yes, that's fine. So did everyone agree with my basic blocks that I've quickly done? I have to check that I haven't screwed it up. So we can sort of think about like these are useless. These don't really mean anything. If, else, yes, right? So let's draw this graph, the control flow graph for this little piece of code, right? Oops. So we have basic block, we have B1, and this is I equals 0. Then we have B2. B3. B4. B5. To make this a bit smaller, how do I zoom? It's not doing anything. Thanks for nothing. Anyway, we'll just be able to squeeze it in here. B6. And so we'll put in some bit of this, will have the while loop. This is the if. This is my J++. This is my K++. And this is my I++. So then we'll think about like a control flow will be, we'll always go from that down to while. And the while loop, if it fails, what's going to happen? It'll go to, we're going to need some sort of extra block. We'll need some B7, which we don't know what's in it, but this is essentially whatever comes X7 is the rest of the next whatever it is in the program. So this is one possibility. Because if we don't take the while statement, like if, actually, well, in this case, we have to take the while statement. There won't be this down because I always got set, but we'll need it at the end of this iteration, right? And so this is where the logical constraint comes in. We know that we're never gonna do this, and that's what our logical constraint tells us. So B4 should be on the same level, right? Yeah, they should be, yes. That's actually a good point. B4 and B5. Q, input Q, nope. Can I get them all? Okay. And this we don't know, right? And so then the flow is the while loop can go to either, well, it's always going to go to X3. Now the if statement can go either to the J++ or down to here. And then these will both go down to here. And the I++ will always go back up to the while loop. So that should be our control flow if I haven't missed anything. So we can use now we could derive the constraints, the structural constraints like we did before. But then, for instance, the logical constraints tell us, for instance, that we would never have the sequence B1, B2, B7 is not possible. Because this is, because we know, for instance, if we did this sequence, we would give, oh man. My tablet hates being plugged into 3 monitors and using a pen. Would give, what am I looking for? X4. Come on, up here. So this is not allowed, or like better said, valid, right? This makes sense where the logical constraints come in. Like when we're solving this, the logical constraints will tell the solver that the path B1, B2, B7 is not allowed and we shouldn't take it. Like it's one of these infeasible paths. Right? And so this is how this constraint would come in to help us or help the solver solve the optimization problem that we want to do. That makes sense? Awesome. Okay, let's go back down to where we were. We've done this. We won't do any logical constraints. And now we'll get to the, well, this is what this is where we should have written the constraints. Here we can see them actually. Where's my move across a bit? This is what we came up with before together. Logical constraints. Here. Someone smarter than us found them for us. So the outer loop here would be I. Okay. But I won't ask you to do this. I think this is a bit too challenging because even for myself, I probably need to really sit down and think about this for a while to come up with these. Okay, so now what I did with the guys last year was we sort of made some more examples from these. So if I want to take this slide here. So can I copy this one? Copy current. Yes. Let's make a couple of them. So now I want to turn this into a cache flow graph example. And if we look at the lecture slides, down here somewhere, we see a cache conflict graph. And so to do a cache conflict graph, you need to know on which cache line your basic block would fall, right? And so we should know now from yesterday what a cache line is, right? It's some block of memory, and your basic block might be made up of multiple cache lines, meaning like if your basic block is, let's just think about, no, cancel. Just an example, if BB0 had 200 bytes of instructions, and your system had 16, or let's say like the standard 64 byte cache lines, then you could need, what's the maximum? So if we have 64, 128, and then like one something, I think you could need up to 5 cache lines to load BB or BB0. Because if we think about in memory, like if we had basic blocks cache, the instructions in memory. So this is the like memory addresses. This is BB0 instructions. This is memory. And let's say that we had the boundary of the first cache line boundary after the first instruction. So this is the 0th instruction. Then we'd have 64 bytes in the next cache line, 64 bytes in the next cache line. So this would give us 128, so 129 plus 64 in the next cache line. I have to post this in. 129 plus 64. So this gives us up to here, we could have 193 instructions, and we would need then the next 7, like this would be 7. Okay, so this would need at most 1, 2, 3, 4, 5, exactly. So we could possibly need 5 cache lines to store this basic block. So this is just one thing that I think hopefully everyone should sort of understand, because we'll see this a bit later why this is important. But now you can't draw a cache conflict graph unless I tell you where on which cache line the basic block falls. And so in the exam, if I ask you to draw a cache conflict graph, I will somehow annotate it to tell you which cache graph the stuff falls onto. Like we saw, for instance, in the lecture here, like you can use colors to annotate them, right? But the cache conflict graph, we have to essentially take then our basic blocks, look at the cache lines they sit on, and then we're going to look at how we can go through how the program would execute in terms of each individual cache line, and look at when we would get the same cache line getting used multiple times without being reloaded, meaning we'd get our hits. And so we can look at how many times we get hits. So this isn't quite sure to you. Hopefully after the example, it'll be a bit clearer. So we'll ignore this for now. And let's just say, for demonstration purposes, I will annotate this graph with some colors to give us the cache lines. So let's just say we have 2 cache lines. We have yellow and we have red. So I'll make this guy yellow, this guy yellow, this guy yellow. And I'll make red, meaning that the code from these basic blocks maps into like the yellow cache line or the red cache line. And so when we want to come up with a cache conflict graph, you have to draw a cache conflict graph for each cache line. So I'll probably either ask you, okay, we have 2 cache lines or 3 cache lines, because I don't want you to have to draw 128 graphs or something. It's a bit stupid. But now a cache conflict graph essentially has the form of like some start, like we'll have some S node, oops. I want black. Some start node, and you'll have at the bottom some end node, right? And this just represents the end and the beginning of the program, or like the code that you're analyzing. So this doesn't necessarily mean BB6. Like this end, these are not the same, this one and this one. This is just sort of an entry point and an exit point from your cache conflict graph. But now we want to look at, for instance, here, we'll do on this side here, we'll do, this is yellow. And then we'll do the same thing. Oops, pen. Oh, I hate my screen. We'll do another one here, start and end for red. So would anyone have an idea how I would go about starting to draw this cache conflict graph on the left? So when we draw these graphs, we are drawing them with only like sort of caring about the one cache line, meaning I am looking now for essentially the transitions to basic blocks. Like I'm drawing a basic block graph, the control flow graph again, sort of, but I'm only focusing on the yellow basic blocks, right? Because they are the basic blocks in the yellow, like the yellow cache lines graph. So where would I go from S on the yellow cache graph? Anyone? So if I'm starting my program up here, where would I land on my yellow cache line? Where's the first like L block, meaning the first chunk of cache on the yellow line on the yellow cache line that I would land at? Which is? Okay. So this diagram is also, these tutorial notes are online. So this is in the tutorial folder. You would find this under, I think it's called worst case execution time analysis, and you'll have this same diagram that you can reference. But you'll just need to somehow color it yourself, or just keep note that I've colored it just yellow, red, yellow, red, yellow, red. But so this first BB0 would go then to BB0. This would be, for instance, BB0, right? Because this is a yellow cache line block here. And so from BB0, where would we go? Like, what are our options? If we're thinking sort of the similar to the control flow graph, where could I be going on in my program's execution? So from BB0, if I'm looking at just the yellow cache line blocks, meaning when I say cache line blocks, I'm talking about L blocks. So this is what L blocks means. I could either go to BB2, so this is a terrible 2, or down to BB6, right? And so we can draw in the flow. So we'd have an arrow here, BB2, or down to BB6. Can you see this? Now, where could I go from BB2? Well, because if you just look at the graph on the left, I'm looking at yellow blocks. So this is, I know yellow is bad, but if we're looking at where I can go between yellow blocks, I can either go down to BB2 or I can go to BB6 because of how the program's flow can go. And we can also see this from, like, it's from our control flow graph, which is the same thing, actually, yeah. So we're just looking at where I can actually jump from which, yeah, okay. So with that in mind, where can I go from BB2? Anyone? So I can go down to BB4. We see this, why? Why is it that you go from just going to BB6? So you think about your program's execution, we're at BB0, like we want to draw the connections between the yellow blocks, but we still think about the actual flow. Like the program can still hit that while loop and go to BB6. But we want to draw a graph that shows the transitions between the yellow blocks, the L blocks. So the while loop could still send us to BB6. So we have, does this make sense? How we're sort of splitting the graph? We're still interested in the complete control flow of the graph, but we're essentially splitting the control flow graph into two subgraphs that are interested in the yellow blocks and the red blocks. Yes. So if you're looking between B0 goes down to the while loop block, it can go through to B2 or it can go down to B6. But we obviously don't draw BB1 on our graph because it's not a yellow block. Right? So if we think about this, where can BB4, or like, sorry, going back to BB2, where else can BB2 go to? I'm hoping you can see that it's all pretty obvious that BB2 can just go down to BB4. But where else could I have an arrow from BB2? This is a tricky one. Very good. So if BB2 was to go down to BB3, the while loop was not valid, we'd go to BB5, then we'd go up to BB1. If it was not valid, we'd then go down to BB6. So we do this big loop. But this gives us a transition of this. So this is the next transition on our graph. So can you then tell me where we could possibly go from BB4? Yep. Where else? BB2. Yep. Now my graph, cache graph, is missing 2 loops. And these are the most important ones. What ones am I missing? So imagine I'm at BB4, and I go back up to BB3 to the while loop, and it evaluates to be true again. Where would I go? Nope. So if I'm at BB4 here, I go back up to here, I can go back down to BB4. I can loop back on myself. So BB4 has a loop like this. Similarly, BB2 can go like this, back to itself. And these are very important because these loops represent cache hits. These guys are guaranteed cache hits. And do we understand why? Like, does it make sense that they would be cache hits? Because each one of these basic block circles represents some chunk of code, right? Somewhere in our program. But all of these chunks of code, because we're using direct mapped cache, they all map onto the yellow cache line. So they all use the same cache line. So if we have BB0 loaded into the yellow cache line and we want to then run BB2, when BB2 goes to run, it's not going to be in the cache line. BB0 will be in the cache line. So we'll have a miss. Yeah, so a loop guarantees a cache hit, but we'll see. So let me finish explaining this and it maybe makes sense why. So BB0 is some program code. It will get loaded into cache. Like at the beginning of our program, we will load BB0 into cache, into yellow cache line. Then let's say if we go to BB2, BB0 is in yellow cache. Therefore, miss. This is a cache miss. That makes sense so far? Because the wrong data is in our cache line. We have BB0 in the cache line, but we want BB2. But there's no way that would have BB2 in the cache line if we've come from BB0. Right? But then let's say if we go to BB2 again, then BB2 is still in yellow cache line, therefore hit. And this is represented by this loop because the last code that was executing that used that cache line was the same code. Therefore, it's guaranteed to still be in cache, which means that we have a cache hit. But if we go from like BB2 to BB6, then when we're running BB6, the last code in cache was BB2, and therefore it's not the code we want, and we'll get a cache miss. So we can say, this is a cache miss. This is a cache miss. Now, there are exceptions to this, which we'll see, but in this case, they're all misses. But the loop is guaranteed hit. No, yellow is the cache line. All of these basic blocks use the yellow cache line. This is why it's annotated. I'm putting the colors to tell you which cache lines these basic blocks map into. Because with direct map cache, every chunk of code maps into one cache line. And so in this basic example, I'm saying each basic block fits into one cache line. Is there a possibility? Yes, there is a possibility. And we'll see that later, but not in this example. Yes. Imagine that these addresses of the basic blocks are somewhere in memory, and the memory blocks that are these basic blocks have memory addresses that have the index of like whatever the yellow cache line is. But I'm just annotating it with these colors to sort of say, imagine I have two cache lines and these basic blocks map into these ones to keep it super simple. Right? And so let's go and do the cache conflict graph for the red nodes, because we have to do a cache conflict graph for each cache line, and we have two. We have the yellow one and we have the red one. So where would my S on the red cache line graph, where would my S block go to? Very good. And then where would I go to? It's one option. What's my other option? No, if BB1 can't go to BB5 without going through BB3. But where else can I go from BB1? Oh, I should have mentioned that this goes out here. Yeah, it just exits, meaning it goes to something after the end of our program. Same as like here, I forgot to draw it in before, but on the yellow cache line, on the yellow graph, we also have this arrow at the bottom because BB6 will go out to whatever's next. So BB6 will exit. So what would I draw next in my red cache conflict graph? BB3 loop. Yeah, good one. And what is that? Very good. There's a guaranteed cache hit. So what is missing then from this cache conflict graph? Yep. What else? Let me see if that's everything. I would say that's everything. So there we have our cache conflict graph for this sort of example, right? And I want to make it a little more complex. And we'll do the following. I'll take the exact same graph. So isn't there a loop BB5? No, because BB5 would go up to BB1. It can't go back to itself without going through another red block. Yeah. So we'll make this a little more complex. And we'll go yellow, complete block, and we'll say, for instance, for this basic block that actually uses both cached lines. And what this means, is if we think about in memory, so this is like memory. And this is BB3 instructions. All it means is it's somewhere, like this is lots of memory chunks, like memory addresses. Somewhere here, like the basic block might be too big to fit onto one basic block. So for instance, to one cache line. So this portion goes onto the yellow cache line, and this portion goes into the red cache line, meaning that this basic block actually uses both cache lines. And so this makes a few things different when we draw our cache conflict graphs. Namely, BB3 will exist in both graphs, right? But when we're drawing a cache conflict graph like this, what's important is we then reference these nodes. These here are not actually basic blocks. I was using BB1 because in this case, every basic block fit onto one cache line. So, which means for this example, B basic block was equal to the L block. But an L block, if we look at the lectures, which will be defined somewhere here, hopefully. L block, L block, L block here. Groupings. These groupings we looked at are dependent on the cache lines. No, where's it more of a definition? Here. Here we go. This is what I wanted. If a basic block maps onto L cache sets, it is partitioned exactly into L smaller blocks. And as we can see here, in the basic example, each basic block is divided into one smaller set because of how many cache lines it uses. So therefore, each basic block was one L block. But in this example, this basic block 3, BB3, uses 2 cache lines. Therefore, BB3 is comprised of 2 L blocks. One is for yellow cache. One is for red cache. So this means it's the portion of the basic block's code that lands on that cache line, because we know that the behavior of that block is always the same. Like the yellow cache, like the yellow portion of the basic block, the hit or the miss of it is independent from the red portion because it uses a different cache line. And so we need to separate into smaller groups where the hit and miss characteristics are always the same. And this is why it's split into 2 L blocks. Does this make sense? I think this is going to confuse the shit out of a lot of people, actually. So if we look back to the lecture notes, we want to group our instructions, like the whole idea of doing this sort of worst case execution time when we're dealing with caches is to group instructions into a group where they share the same hit and miss characteristics. And the smallest groupings that we can do is the chunk of code that falls onto the same cache line, because the hit and miss is not dependent on the basic block, but it's dependent on where it maps into cache. And so the smallest grouping that we can do is to put it into blocks of instructions that have the same, I wonder if it's written here anywhere, the same cache line. And if we look at our example, BB3 has to get split into 2 groups because one portion is dependent on the yellow cache line and one portion is dependent on the red cache line. So we have to group it into 2 what we will call L blocks. And these L blocks are the blocks that are like line blocks, meaning they're the blocks of the cache lines. So the BB3 has a portion of code that executes on the yellow cache line as an L block, and a portion that executes on the red cache line as an L block. So maybe if I do the graphs, it'll become a little more apparent why we actually use L blocks and not BB basic blocks. Yeah, so the code for BB3 could be more, if it's larger than the cache line size, it might use more than one cache line. And in this example, as you said, exactly, Elliot, BB3 is using 2 cache lines. Now, the fact that it's a while statement is probably actually not going to be 2 cache lines, but just for example purposes, we're saying that the code in BB3 is so big that it takes up 2 cache lines. So we have to do the same thing again. We have to create two graphs. What was this? Nope. So we're doing a start, and a start. I have to make these a bit small this time. Don't have as much space. And exit. And so this is again the yellow graph, and this is the red graph. So yellow graph, you guys should be able to tell me the first couple of blocks, easy peasy. But actually what we'll do, sorry, before is actually we should go and we should give, because we can no longer, we shouldn't reference them as BB0 because we actually need to split them now into line blocks. So we need to say, like, for instance, this is like, we'll say, oh man, 1, 2, 3. Now this one is 4 and 5 because like this yellow one is 4, this red one is 5. So I can probably even make it more explicit, and we'll say like 4, 5, 6, 7, and 8. So these are our L blocks. Where's my... Meaning we're now looking purely at the cache line like we were doing before, but we just, because one cache line was one L block, we used the BB, the basic block number to reference. So I'll use what you said before, which is, we'll just write it a different way. So we'll have 1. Now 1 can go to basic block 2. Yes, so this is to 3. To basic block 4, which is 6. So we're going to have 4 in here as well. We have 6 in here as well, and we have 8. So if we put in all of the L blocks, similarly, we can just do this straight away at the beginning and put them all in. 2, 5, 7. I think we have 1, 3, 4, 6, and 8. Okay. So Miss Elliott's 3 to 4. Yes, correct. And 6 to 4. Yes, correct. I think there should be a few more in here. Yeah, there is a few more. 4 to 3. Yeah, very good. 4 to 3. So we're missing pretty much just this one up to 8, sorry. 1 to 8 and 8 to exit. Yep. I think that's all of them. But we can see now, for instance, it looks a little bit different. Like we no longer have this connection from what would have been, where was it? BB6, oh wait, BB. Like for instance, we no longer have this BB2 to BB6 connection because this the L block 4 has sort of interrupted this, right? But now, do we have any loops in here anymore? No, we don't. So we have no guaranteed hits. But now we need to think about something a little logically because there is a potential hit in this graph. Can anyone tell me which line of this could potentially be a hit? Which would require a bit more analysis, but there is a possibility in this left-hand graph, this yellow graph, that we would have a hit. Four to 6. 4. Yes, I am. Indeed. Well spotted. I think that should be everything. Although 4 can 4 go down to 8? 4. Oh yeah, I'm missing 4 to 8 as well. 4 to 6. So I think now we've got everything. But one of these arrows could potentially be a hit. Which one? Four? Which one? Which arrow do you mean? There's a lot of arrows with 4. The return arrow from 6. No. So if we think about the code, like let's think about this is the code for, we sort of had it here. Let's expand this a little bit. So this is memory. And let's just say like this point in time here, this is the end, this is BB3. This is BB3. And this might be, for instance, BB2. And this whole section might map into cache line. So because you can see here, we have this transition, sorry. Now this might be a bit confusing for people to sort of grasp, but here, this transition, or this edge, this this L block transition means L block 4 is at the end of a cache line. Because the basic block is sequential instructions. So they cannot be interrupted, meaning they have to be sequential in memory. Meaning that because we have this yellow to red transition inside of a basic block, that the yellow block sits at the yellow L block is at the end of, like it's the end of an L block, and it will then continue on into the red L block, which makes up BB3, which means that we can know that this is how our basic blocks look in memory. At least we can confirm this, like this transition here, this green line is this green line here, which can mean that basic block 2 sits in, it could potentially sit in the same L block or the same cache line as BB3, meaning when it's loaded. Basic block 2, the code for, sorry, I shouldn't say basic block 2, the code for L block 3 here, this guy could potentially be here, which is in cache, which means that we could potentially get a hit here. Now it's not confirmed hit, so a loop is guaranteed a hit. It could be a hit, because it could also be that BB2 is somewhere completely random in memory because the compiler put it somewhere completely different. But it could also potentially be just before the L block 4. These could be in the same memory chunk, potentially. So this is a sort of an asterisk hit, pending more investigation. So I'm hoping this makes sense. It's a bit confusing. The key thing to know is that we can establish this green line because of basic blocks, how they can't be interrupted. They are continuous instructions, which means they're continuous in memory. So it means that since they're continuous, that the fact that we have yellow and red in the same basic block means that we actually are going over the end of the yellow cache line into the beginning of the red cache line. And why we don't get a potential hit between 5 and 7 is because we have some yellow code between it, which means that in memory, if we were to sort of make, like, let's say, take orange and say like, this is orange, this would potentially sit here somewhere. And then if we take like dark blue, this would sit here because they're in memory. And so we can't potentially have them in the same cache line. And so there's no hit there. Okay. So then let's go on and draw the red cache conflict graph. We have 2, 5, and 7. So looking from the left, who can tell me my transitions from S? Yep. What then? 2 to 5. Perfect. Yep. 2 to E. Yep. Very good. And so what's special about that one? This is a guaranteed hit because it's a loop. Guaranteed hit. Possible hit. Yep. You sunk my battleship. So I think that's sort of everything we need to cover from the cache conflict graphs, basic blocks, and whatnot. Hopefully we can sort of see how we would partition our code into our basic blocks and derive the structural constraints as well as the logical constraints. And this is sort of what you would then pass into your ILP. Similarly, you can also derive structural constraints from your cache conflict graph in the exact same way. We just look at each individual graph in itself. We can say, for instance, like, oh, this is like this would be, give it some value like A1, and we'd say like, yep, A, and they'll say this is like A2, A3. We can say, the same thing again, A1 equals A2 plus A3, and you can derive structural constraints. I'll upload this after this. And then all of these, what you sort of need to know is that we don't solve these. We use linear solvers because it's a very complex problem. Like we use specialized programs, but we derive these linear constraints and these linear equations, and we feed this into the solver, and then it will solve it for us. So we need to know how to derive this stuff to model it, and then we feed it into the solver, and we're good. So any questions? Otherwise, we're pretty much done for today, nice and early. Yes. Because we can know, for instance, we model our hardware and we can then find out our hardware can tell us X3, like X1 comes from hardware model. This is telling us like X1, where is it? Is some set of instructions. Therefore, it has some execution time. And so this is sort of like the one way of doing it. And then the whole idea of these L blocks is that we then break it down one step further. And we then have these execution times that are based off of hits and misses. And so when we look at the slides, we sort of take it one step further and we get here. The worst case execution time is no longer just the sum of, it was way, way back, I think. Where was it? Is no longer just the sum of the execution of the basic block times by the amount of times, but it's actually the sum of the cache hits and misses. And so we don't go too far into this sort of in-depth analysis because it's a bit more complex, but we can at least start to break down our program's execution into each cache line's activity. Because then we can, for instance, we can know, for instance, that we could say BB2, like there is this BB2, oh, sorry. So that if we were to say, let's look at this function, the equation, is this the number of hits times the execution time and the number of misses times the execution time. And so, for instance, we could say like x2 equals like the hits plus the misses. And we know, for instance, let's just say like A5, we know A5 is a miss, sorry, a hit. And so if we were to complete this formula, it would come into the hits portion. But we don't go into this in depth, right? But this is why we start to break it down, because we can then, for instance, in the future, derive more constraints and more, and then solve the problem on a lower level, looking at the cache activity rather than just the basic blocks. But we would need another week to do this, and you'd probably need a better lecturer than me. Okay, then I would end it there unless anyone has any questions, and we can pick it up at the tutorial time, and I'm just going to go and try and find old exam questions. We'll be doing a sort of a wide mix of things. There's no plan for the tutorial. Essentially, just ask me questions. I'll find some old exams, sort of go through what you should know so that you can think, oh, I don't know that. Can you quickly explain it again? This sort of thing, like a recap in 1.5 hours. So it should be interesting.